Yes, recording. Let's calculate it. Thinks a little bit. It has to think a little bit. It's going to take a little bit longer for the TI. He has a hard time. He has a difficult time. It's a much, much nastier formula than the Z distribution. Okay, here we go. Let's make sure we know what these numbers are telling us. Well, they tell us this and this, which we already knew, and that too. Basically, it does one bar stats for you, which is extraordinarily convenient, but nice and happy, but unnecessary. Because what I really care about is that. That's what I really care about, yeah? So, what is this telling us? So, in our class of 27, the 95% confidence interval for the number of times we got correct results. I know, thrilling. Out of 10, this is out of 10 trials. Out of 10 trials, the number of times we got correct results out of those 10 trials is at least, looks like 5.2, or at most, about 6.8. So I'm going to ask my question again from before. Now that you know the answer, I want to make sure you can identify the answer. Is our margin of error smaller or larger than S? Is it smaller or larger than S? I got a very quiet vote for smaller. I think I heard some back there. I'm assuming that was smaller. They're going to be showing me smaller. Good. What is your margin of error? Ish. What is it?
0.8.
Yeah, it's about 0.8, isn't it? Your average is about 6. And that average is in the middle of this interval. You got to remember, and when I say remember, I don't mean this formula. I don't mean this, I'm about to write a formula on the board. I don't mean to remember this formula. But remember how it's calculated. The confidence interval is X bar plus or minus the margin of error. That margin of error has a formula. It's T times S over root N. We looked at it last week, and you can forget about it because the TI is doing it for you. But that X bar is in the middle of that interval. So if you need to know what the margin of error is, just look at X bar, which in this case is about 6, and then go down or up to one of the endpoints. And that distance is one margin of error. So it's about 0.8. So it's definitely smaller. Why does it make sense that it's smaller? Why does it make sense that it's smaller? Because the sample size, right? As your sample size goes up, your margin of error should go down. That's the whole definition of the inverse nature of sample sizes and how they're related to margin of error. Central limit theorem. As your sample size goes up, margins of error go down. Makes perfect sense. That's why I want to look next at the overriding class result, which you can't see because I'm putting it on the screen. I want to look at this too in a minute. We'll come back to that though. So the first question I have, actually is it the next question? Let's see if it's the next thing I asked. Is this confidence interval evidence? I love this question. Is it evidence of the existence of, or our ability to detect, the energy field? Why or why not? What do you think? What do you think? Does this show us anything? Does it show us? Veronica's saying, yes, it does. Expand.
I was trying to give someone else the chance.
Oh, you're trying to give somebody else a chance. Veronica has said yes. Who agrees with her and why? Who agrees with her and why? Who says yes? This might be evidence. I'm not saying proof. I'm saying evidence.
Is it because the margin of error is greater than 0.5?
Or 5 in this case. Thank you, Melanie.
Yeah.
Yes, just 5. I love what you're saying, 0.5. That's the half percent, the 50% of the time we would be guessing. But if we did 10 trials, we would average 5 correct. Exactly 5 correct. If we were guessing, yes? Let's make sure we understand that. If we were guessing, like I was doing, honestly, I had no idea where anybody's hands were. Left. If we were guessing, binomial distribution says we're going to get half the trials right and half the trials wrong, which would be 5. Well, look what we're doing. Remember how excited I got when I saw 6? I'm like, and then, of course, 6 by itself doesn't tell us anything. You have to slap a margin of error on the 6. But even after we've slapped the margin of error on the 6, what happened? It's still higher than 5. Now, is it meaningfully higher than 5? I don't know. I put my arms up. I don't know, maybe. It might be. But it is statistically significant. It is statistically significant. Check it out. Draw it. If you want to Here's the number of correct responses. Out of 10. Out of 10. Number of correct responses out of 10. I should move the camera so we can see that. Because we don't need that big blank screen anymore. There we go. So the number, and this is actually getting pretty close to what we're doing the tail end of today, moving into the rest of the course. The number we want to compare that to is this 5. Oh, you can't see that, can you? It's the 5. Because that would be the average number we get right if we were guessing. If we were guessing, that would be the correct number. And the wrong number, we guess 5. And we get 5 wrong, get 5 right. But our evidence, our results that came back show slightly to the right of that. Yes, our minimum is about 5.2, our maximum 6.8. Which means there is a little bit of a difference, isn't there? There is a little bit of a difference. And what's that minimum difference? About 0.2. About a fifth of a guess better at least. That's one of those MMDs, yes? One of those MMDs we talked about, the minimum measurable differences. That would be a 1/5 of one question correct minimum measurable difference. To which anybody that understands precision would say, I call BS on what you just said, Roll. Because you round this to a decimal, maybe you should have rounded to a whole number since everything else was whole numbers. In which case it would go 5 to 7, and we couldn't complain, we couldn't compare anything. That's okay, that's alright, that's totally fine. I want to go back and look again at the entire results over time and see how that stacks up too. Stacks up too. Stanks. It's a new word. Stanks. Fair though? You see though, if we round to a decimal, we pick up that 0.2, at least a 0.2 difference. That is what we call statistically significantly different. It might not be practically significantly different, but it's statistically significantly different. Fair enough? I can't argue practical significance. I never can. In order to argue practical significance, I have to have expert knowledge in whatever field we're studying. In this case, I don't know what the hell this case would be. What field would this be in? Psychology? Kinesthesiology? Biology? Metallurgy? I don't know what it is. But all I know is numerically, there's a statistical significant difference. At least a 0.2 improvement over guessing. Now, of course, we can poke holes in this all day long, yes? Of course we can. For example, how many of you could feel when your partner's hand went over yours? Moved air? I've heard that from a few students, that when they put their hand over your hand, they do it so quickly that air moves. Which means you would then have a better idea of where their hand is because you felt an extraneous force indicated. So that's one experimental criticism you could have. Something else is heat. If you could feel their hand's heat over your hand, that would kind of negate the energy field, unless your energy field is defined as heat, in which case it doesn't. But I don't think it's defined as heat. So there's all kinds of experimental reasons you can kind of pick holes in this. Not to mention the precision problem, the 5.2 versus 5. So what I'd like to do, I know that's all for the quiz. That's all for the quiz right now. But I want to go back in. Let's go back in and use the numbers from the cumulative results we've seen